We are the solid state Marx team. My name is Patrick. I'm joined with Philip, Braden, Ethan, and Marcus. A solid state Marx generator is similar to a typical Marx generator, except it uses solid state switches in place of spark gaps. It uses a capacitor, transistor driver, and isolation elements between the stages. A lower voltage power supply is used to charge the capacitors in parallel. When the capacitors are charged, the transistors are switched, connecting the capacitors in series, which results in an output pulse whose voltage is n times the charge voltage, where n is the number of stages. Our 5-stage Marx uses 5 kV as a input pulse for a nonlinear transmission line team.
So for the background, Marx generators are a type of pulse power device where energy is stored in slowly over time in the capacitors in parallel and then discharged all at once in series. So the Marx generator is used commonly in high-powered lasers, particle physics, radar, and in electronic warfare. Isolation is done between each stages using either resistors or inductors to force current through the switches, and in our case, we're using resistors. The first Marx generator was the spark gap Marx generator, which uses resistors as the charging element and spark gaps as the switching element. However, the solid-state Marx generator uses MOSFETs, or solid-state switches, as the switching element. Using the solid-state Marx generator, it reduces the overall voltage to tens of kilovolts, but the compact design and easy to control nature of it makes it very attractive.
So for our requirements, the solid state Marx generator is taking in a 1 kilovolt input and putting out a 5 kilovolt pulse. And to achieve this, we're using 5 stages. And it's going to put out that pulse through a 100 ohm nonlinear transmission line.
So when we were simulating under ideal conditions, of course, but we added some resistive and capacitive elements to give it a more realistic representation of what our actual circuit would be like. So you can see our actual simulation model in figure 6, and in figure 5 you can see the output voltage that we were getting. With a 1 kV input, we were able to get 3.6 kilovolts at the output, and this simulation was mainly just to get the capacitors resistor values that we needed. We then selected components and started building.
So we started out creating a small scale prototype to test our driver circuit that's shown in figure 7. And as you can see, with 24 volt input, it was able to produce 120 volt output pulse. So that proved that our driver circuit would work for this scenario. After that, we scaled it up to using high voltage components. We had some issues initially. As you can see in figure 9, the output pulse was not a single pulse, but multiple pulses. We determined that that was because there was a propagation delay between when the module would receive the signal from the FPGA to when it would actually fire. So we were able to offset that using the FPGA and get a nicer pulse. However, that was at 50 volts input. Once we started scaling up to around 200 volts input, we began to have an issue where the MOSFETs were switching off before the capacitor was fully discharged, and that's shown in figure 11. So we're not 100% sure what's causing that, but we have created a new design with more isolation, and that should hopefully fix that issue.
So we were able to successfully create a 5-stage solid-state Marx generator that multiplied the voltage. However, we weren't able to test it at 1 kV quite yet. And on top of that, we did run into some timing issues with it. However, there is a concepts team that is going to be taking this over after us who will address some of those problems. And they will also attempt to get a square pulse at the output and use an H-bridge DC to DC converter at the input instead of the 1 kilovolt power supply.